So in the last video I showed you guys about like array lists. Now in this video I'm going to talk about a different data structure called linked list. Now array list, if you remember, uses an array as its backing data structure. And arrays inherently are pretty wastely in terms of memory because they have to pre-allocate all of the available memory at the beginning. But a linked list is a nice way to avoid that problem. But then other cons come up because of it. So after you learn how this works, you'll start getting an idea of how data structures are just basically tools in a big toolkit that you use in the real world. So a linked list, in general, is just a bunch of nodes chained together. So a node, I would say, so let's see, a node, it would be an entirely separate class where it would have two instance variables. One instance variable, I'll do it like this. So one instance variable will be of type E, and I'll call it val. So this first instance variable is the actual value of the node. Then it'll have another one, and this one's a pointer of type node that's called next. So basically each node knows two things. It knows its own value and it knows what node comes after it. It's basically lining up a bunch of people and telling them like, oh, this person is after you, this person is after you, and then getting them to line up. It's just a bunch of random nodes that each only knows its own value and what's after it. So a linked list has, well, just as a data structure, we know it should have some size instance variable that's a type int that we can just return using our size method. It keeps track of every time we add an element, it'll increment, and every time we remove an element, it would decrement. And then returning it via the size method just tells us how many elements are in our list at any given time. So that's that. Then with the linked list, this might not be as intuitive as the array list, but realistically all we need is a pointer of type node that's called head. So there's three different main approaches to using linked lists. The first approach, which is the one that I'm going to be talking about in this video, is where your head is pointing to the very first element in your list. So right now, when I create my list, head is pointing to null, which means there's no elements, so there's no nodes. There's other implementations where maybe you'll have a dummy node, so maybe you won't have a value, but the next will be pointing to null, and then every element after that starts from this dummy node. And then there's another third implementation where you have a dummy head and dummy tail. So the third implementation might be useful for being able to traverse your linked list from the end or the beginning, but this is generally the easiest way to do it, and it's what I'll be doing. So yeah. So my add method. How would I add a node? So I have this pointer. I'll do these ones in green. So I have some pointer called head, and it's not pointing to anything. So the way the add method works with a linked list is I create some new node, and then I put in my value, so I'm going to say like 1, right? And then next is null because I don't have some next element. And then my add method is then going to go through my linked list, and then the first available empty next pointer, it's going to point it at this new node. Does that make sense? So at the end of the add method, just before it finishes, I would have 2 pointers, each pointing to it. One of them is the instance variable, one of them is this local variable from the add method. Then when the method call returns, local variables, as we know, get destroyed, and all we're left with is this single pointer from head to this. It could be any, whatever the last node was is now pointing to this new node. So if I do the add method again, it'll create a new node. Let's say I do add 2. It creates a new node of value 2. And then step 2 of my add method starts at the head, keeps on seeing until the first open pointer, and then it points that to my new node. The method call returns, and then I'm left with this. So I'll do it one last time. Let's say I'm adding 3. So I make a new node. You know, Java, object-oriented programming, everything is a pointer. It has 3. Then step 2, start at the head. This is filled. This is filled. Ah, this is empty. I'll point that one to my new node. The method's done. Now it returns. Local variables are destroyed. And this will be how my linked list would look like after 3 iterations of this. And size will now be 3. Right? So then that's pretty much how we add to the end of a linked list. Yeah, so what about if we wanted to add to the beginning? Adding to the beginning is pretty easy. All we have to do is I would just create some new node. Let's say this one will be 4. So it has value 4. So you just think, how would we do this? So if I want this to be my new first element, I should point this one's next to whatever head is pointing to. So head is pointing to this, which was my first element. Now my new node points to that same thing, and then my head will now point to that. So it's like a 3-step thing. We create the node, set its next to the first element, and then set head to this new one. It's kind of like a triangle business type thing. So then what's the result? The results would be, I'll just redraw the whole thing. So head is our instance variable. It points to what is now, it was the new node. Oh yeah, and then method call returns, the thing gets destroyed. So that points there. Right, head points to that. This points to there. And that points to that. And that points to that. So as you can see, that's how we add anywhere into the linked list. So I'll add one in the middle just to kind of show you how it works then. Just one more trick. So let's say I do something like add, let's say I want to add an index 2, so that's the third element, and I want to add new integer 5. So I want to add an integer of value 5 at index 2. So what happens, my add method, as we know, we start at the beginning, and we have to cycle through until we reach the point before my insertion. So let's see, I start here. This is the first index. I mean, this is index 0, this is index 1, this is index 2. So I have to stop here. Okay, I create my new node. new node is pointing to some object I just created of type node, where it has 5, right? I created an integer object as the value. Now, I told you I have to go one step before my insertion. So if I'm inserting at index 2, I have to stop at index 1. Now, whatever my new node's next is pointing to, so new node.next equals whatever I stopped at .next. Does that make sense? So I want this thing's next to point to whatever its predecessor's next was pointing to. Right? Because if I'm inserting it here, that means my net outcome, I want this to point here and this to point here. So I have to first point there, and then now I would point here. So then the net result would be, let's see, this is head for 1. So this points there, this points there. Now this one points here. 5. That one points there. That one points there. Now, one last example. What if I want to remove an element? So let's say I do remove 0. So what happens? If I'm removing, actually I'll do remove 1, just to make it a little more complicated. So what happens? So let's see what my index 1 element is. This is index 0, this is index 1. So I want this element to disappear. Well, an easy way to do that would just be to point this here, right? Which we can do. So if I call this, all I have to do is start at the head, cycle to the point before my deletion. So I'm deleting this, so I stop here. Then I repoint this thing's next there. What happens? This object, even though it still points to something, it doesn't have anything pointing to it. Remember, in Java, garbage collector deletes anything that doesn't have a pointer pointing to it, because otherwise you can't access it at all. So this, even though it's pointing to other stuff, I can't call on this itself, because nothing points to it. So then, once I finish my remove method, garbage collector will clean this up. And then my net result would be head. So head points to here. Now this points to there. 5 points to 2. 2 points to 3. There you go. So we just did a couple of nice little add and remove stuff, right? Pretty easy. So now to analyze the efficiency of this. Because if this was always more efficient than an array list, why would anyone use an array list? It wouldn't even exist. Because array list is costly in terms of memory usage. While this linked list, as we see, every time we add an element, we create exactly enough space, and every time we remove an element, we delete whatever memory it was using. So my linked list is only using just enough memory as it needs. So what are the problems? So I'll talk about pros and cons, and then let's see, I'll talk about pros in blue. So pro, you saw if I wanted to add to the beginning or remove from the beginning, it was an easy one-step thing. No matter how long my list is, I just create a new node, point that to the first element, and then point head to that, no matter how long my list is. So just like how array list was efficient for modifying the end, a linked list is fast modifying front. And then I mentioned time complexity, so I will here again, even though you haven't really learned them. So it's constant time. No matter how big our list is it takes the same amount of time to remove or add to the beginning. That's nice. 2. Memory efficient. So our array list, the backing data structure, that backing array, doubles in size each time we reach capacity. So it starts at 5, then I reach 5, it goes to 10, then 20, then 40, then 80, then 160, so on and so on. So what if I hit like 2,000 and then I fill it up? Now it doubles in size and I'll have 2,000 spaces just being wasted. And that's a pretty big waste. So this, no matter how many elements we have, it uses exactly as much memory as it needs. So that's really nice too. Then I'll make this one red. 3. Slow modifying end. So this is a negative aspect of a linked list. Is you noticed if I wanted to add to the end or remove from the end, I have to cycle through each element until I reach the last thing and then point that to my new node or do whatever I have to do on the very end. So if I have 1,000 elements, I actually have to physically, or not physically, but I have to theoretically cycle through every single 1,000 elements until I reach the end. That could be really slow when we hit large values of n. And the fourth thing, which is also a con, is no random access. So this was a nice feature that we mentioned about an array list, is that no matter what element I want to catch, so maybe I want to see what element at index 100 is. Out of my 1,000 elements, maybe I want to return the value of the element at index 100. What do? I just do get 100, and then the array list calls on the backing array. All that memory is already allocated and whatnot, so it takes constant time to pull that element. It doesn't take like any time. No matter how many elements I have, if I call on one index, I can pull it instantly in an array list. But what about a linked list? If I want to do get on the very last element, what do I have to do? I start at the head, and then I have to traverse all the way through until I reach the last element, and then I can get it. So this is big O of n. So, and this is where I was talking about some implementations would use 2 dummy pointers. One would be a dummy head, and one would be a dummy tail. Where the dummy tail points to the last element, the dummy head points to the first element. So that is a way of trying to make this random access thing a little more efficient. Because what if I'm trying to get the element at the end? Then with that other implementation, it'll take instant, no matter how big n is. Right? So at least it's a way of kind of, speeding it up. So then in that case, the worst case would be in the middle, which then even if I have a header, a pointer to my head and a pointer to my tail, it would still take forever to reach the middle. So yeah, it's not very efficient for doing anything except for at the beginning. So yeah, that's basically a linked list. You'll learn about queues, stacks, and these different types of data structures. A linked list could be useful for a stack, which we'll learn about. But yeah, we'll talk about that stuff later. But that's essentially a linked list. It has these pros, fast modifying at the front, and it's very memory efficient. And these cons, that it's slow at modifying at the end, and no random access, because we have to cycle through all the elements.